Hello and welcome to my video. About a couple weeks ago, I posted this video where I sketched the parametric curve using calculus and calculated the area enclosed by the curve. And the problem is stated in here as well. And you can check that video in top right corner. In that video, I solved the problem without eliminating the parameter t because I considered that as the most general method applicable to the most number of parametric curves. However, for this particular problem, we can solve it in easier way because for this particular problem, we can actually eliminate the parameter t. So here I am going to solve the problem in this way. So first, let's eliminate the parameter t and express the curve as y equals fx form, which is also known as explicit form. So from the first expression, we have t squared equals x over 2. Now notice that x can be only defined on x equal to or greater than 0, so that's our domain. Moreover, for t we have 1 over square root of 2 x to the power of 1 over 2 for non-negative t, or t equals minus 1 over square root of 2 x to the power of 1 over 2 for negative values of t. And if we substitute t from the second equation, we can finally eliminate t and obtain, when t is positive or 0, y equals 3 using this. So we have this expression, and when t is negative, we have to use this one. So we have this and therefore this expression. So therefore, we can write like this using plus minus sign. Now notice that these two graphs with plus sign and minus sign respectively are symmetric with respect to x-axis. Therefore, we only have to investigate the graph on one sign, say plus sign, because if we obtain the graph for plus sign, then the other graph with minus sign is just the same graph with opposite sign, which means symmetric with respect to the x-axis. So now let's investigate this function, which is we take the plus sign. First, let's investigate x-intercepts. Notice that y becomes 0 when x equals 3. This is easy to find. Therefore, the graph passes the point 3, 0. And obviously, it also passes 0, 0. Now, let us calculate the derivative to investigate the slope, hence the increase and decrease of the function. So dy over dx is 3 square root of 2 over 4 x to the power of minus 1 over 2 minus, and 3 over 2 must be multiplied. So we have 3 square root of 2 over 4 x to the power of 1 over 2 because the power is decreased by 1. So this is our derivative, and we can write this derivative as writing constant terms at the front and x to the minus 1 over 2 minus x to the 1 over 2. So when the derivative is 0, it means that this term is 0. And let's multiply x to the power of 1 over 2 on both sides. Then we have x to the power of 0, which is 1, minus x to the power of 1. So x equals 0. So therefore, x equals 1. Now investigating the sign, we know that dy over dx is negative when x is in between 0 and 1. And dy over dx is positive when x is greater than 1. Next, let's investigate the second derivative to investigate the curvature. Using this expression for the derivative, the second derivative is given as, so first the constant 3 times square root of 2 over 4. Then, if we differentiate this part, we have minus 1 over 2 x to the power of minus 3 over 2 minus, and if we differentiate this part, we have 1 over 2 x to the power of minus 1 over 2. And notice that this is always negative, because this part is always negative. So the graph is always concave, like this. And now we can summarize this result in this table. So we have several values of x. And remember, from the first derivative, we found out that the derivative is 0 at x equals 1, and the derivative is positive here, and negative for x greater than 1. And in case you're curious, the derivative actually approaches positive infinity here and negative infinity here. And for the second derivative right here, we found that the second derivative is always negative, so the curve is always concave. And in case you're curious, the second derivative approaches minus infinity when x approaches 0, and actually approaches 0 when x goes to infinity. So the movement of the point x, y is as follows. When x equals 0, the y is also 0. And here the graph increases because the derivative is positive. And here the point reaches 1, square root of 2. And the curve decreases. This is 3, 0, which was the another x-intercept that we have found. And the graph keeps going down to the minus infinity. With this, and using the fact that the graph is always concave, we can draw a curve like this. So the graph passes 0, 0, and then it increases and passes 1, square root of 2, and it passes 3, 0, and this is the graph for the plus sign. And for the graph with minus sign, all we have to do is to simply flip this graph with respect to x-axis, so we have a curve like this. Right, so this is the curve, and now let's calculate the area. Okay, so we have our curve here, and this equation refers to this half of the graph, and the area A enclosed by the curve is this area, but that area is simply twice the green area, and the green area can be calculated as integral of y dx, where x is from 0 to 3. So therefore, using this equation, we have 2 times the integral from 0 to 3, 3 square root of 2 over 2, x to the 1 over 2 minus square root of 2 over 2, x to the 3 over 2 dx. So we have, here we have to integrate x to the power of 1 over 2, so we have 2 over 3 x to the power of 3 over 2. And here we have to integrate x to the power of 3 over 2, so we have 2 over 5 x to the power of 5 over 2. So if we calculate all of this, we obtain 12 square root of 6 over 5. And this is our answer. So here we sketch the graph of the parametric curve by eliminating the parameter t. And again, if you want to take a look at another method where we don't eliminate the parameter t, please check my past video from the top right corner. And as always, thank you for watching, and I will see you in another video.